Okay, so next thing, I want to go over the reduce problem from lab, which is yet another pattern of computation. So the idea with reduce is that um, when we have things like map or filter, they're taking lists to lists, right? So like map takes a list to another list of the same length by applying a function to each element of the list. And filter takes a list to a list with a perhaps smaller length by keeping only certain elements of the list. What we haven't yet done is to write a higher order function that captures the kind of code we often write, where we take a list and then summarize the values of that list in some way. So for example, the two things that the lab asked you to generalize were taking a list and adding up all the elements of a list, right? So if I sum the list 1, 4, 5, then I get 10. Or if I join together the strings A, B, D, then I get ABD. Okay, so the idea of taking a list and kind of squishing it down into a single value by applying some operation. So if we look at these two functions, then the way we think about writing a higher order function from them is we look at the two functions and we ask what's the same and what's different. And I'll call this reduce. Well, the types are different, so we're going to have to make it polymorphic. If L is a list of alphas, sum takes an int list to an int by adding up all the numbers. Join takes a string list to a string by string appending all the numbers. So if we're kind of trying to capture that pattern, we're going to take an A list to a single A, whatever A is. And then we get to case L of empty goes to something, or x counts x's goes to something. Okay, and if we think about what's going on in both of these functions, in sum, we take the first thing in the list and we add that to the recursive call. And in join, we take the first thing in the list and we string append it to the recursive call. So what we're going to need is to somehow capture this information of the caret or the plus as an input to the function. And the other thing that's different between the two is in the sum one, the base case is 0, and in the join one, the base case is the empty string, so we'll also need to pass that in. So the empty string is easy because that's just a value, right? Like here I pass in 0, here I return 0, here I return the empty string. We'll just pass in an input that's supposed to be the 0 or the empty string and call that E. And then the plus and the concatenation are a little bit harder because that's a thing that is new to this week, which is the idea that we can give a function as inputs to as an input to other functions. So what's the type of plus here? Plus takes two ints and returns an int. What's the type of string append here? It takes two strings and returns a string. So in general, the input to reduce is going to take an A star A to an A, which is to say that it takes two A's and gives you back an A. And then the pattern that we're capturing in sum is that we do whatever the way we passed in to combine things was of x and the recursive call of x's. But then the only other thing is I need to specify in the recursive call that it's the same combiner in the same base case as I go through that. Okay, so let's see, something's wrong here. And oh, sorry, combiner is called C, not N. Okay. All right, so now let's do some examples. How do we get sum as an instance of reduce? Well, what we're doing is we're reducing L to a value. The base case is supposed to be 0, and the combiner is supposed to be the function that is given two things and adds them. And so now if I take the sum of 1, 2, 3, 4, 5, I get 15. Good. Okay, so what we're doing is we're saying that here we're giving you the plus function using the idea of an anonymous function that we talked about on Monday, and then we're passing in 0. And if I want to do join, which is taking a string list to a string, well, what I do is I just change what I'm giving as the combiner and what I'm giving as that. And then I say that the way I'd like to combine things now is with the caret, which is the string append, right? If I do ABC, I get ABC, string append there. And as the base case, if the list happens to be empty, then I give back the empty string. Okay, and so, we can do other things. So for example, maybe I want to put a separator in between things. So if I do that, if I change my combiner to be the function that combines things together, but puts a comma in between them, then when I do join together ABD, I get a comma B, comma D, comma, because I'm putting a comma in between the first thing in the list and the rest of the list every time that I do that, the way that reduce works there. And instead of adding, I could up numbers. I could find the biggest one. Well, how would I do that? I'm going to reduce, and so the idea of max L is that if you give a list like 1, 7, 5, 4, 12, 2, whatever, then it's supposed to tell you the biggest number. How do you find the biggest number with a reduce? Well, you put in as a combiner function that you'd like to take the maximum of the first thing and the recursive call on the tail. And then for the base case, what you need is some very small number, right? Because the unit for taking the maximum is a number we're looking for a number where if we take the maximum of it with anything, then we get the other thing. And so what we want there is like negative infinity, or the smallest integer that exists, which is in the SML standard library and called minint there. Okay, so that's just getting that out and binding it, giving it the name minute. Okay, so we can do that. Okay, so the point is now we've got the ability with reduce to kind of squish lists down into a single value. Whereas before what we had was just the ability to like turn a list into another list. And so I want to do another one of these pipeline problems, which is the word count one from lab. So the idea for the word count one was that the goal was to find the length of the longest line in a document. the length is being counted in number of words. So for example, if I had like the quick brown fox and then jumped over then the length of the longest line is 4 words. And why is that? Well, this line has 4 words and this line has 2 words. Okay, and in SML, we'd write this as like the string value that gets printed like that is that with a \n in the middle of it. Okay, so up here, I've tossed in some library code. It doesn't really matter. You don't have to read like what the library code does, but the point of words is that the words of a string is going to divide it up into a list of strings where the entries in the list are the words of the string and the lines is going to divide it up into a list where you get one entry in the list for each line of text. Okay, so how do we compute the length in words of the longest line in a document? Well, we can think about it as a pipeline problem. So we might say, in step 1, we divide the document into lines. In step 2, we count the number of words in each line. And in step 3, we take the biggest. So for example, if that's my document, then in step 1, I would expect that list as having divided the document into lines. In step 2, I would expect, well, 4 and 2 because I count the number of words in each line. And in step 3, I would expect the 4. Okay, makes sense. So what we're saying is I've got my document. Step 1, I divide it into lines. Step 2, I count the number of words in each line. And step 3, I then find the biggest number of those. All right, so get a string as input and output a number. Okay, so now what do I do? Well, in step 1, I said I was supposed to divide the document into lines. Well, fortunately, we already have a helper function coming from some library code up here, lines, that divides the document into lines. Okay, so good on step 1. In step 2, what I want to do is I want to count each of them. Well, you can kind of read off from the structure of the example that what we're doing here is turning each string in step 1's output into a number, right? So we get one number for each string in the list that step 1 returns, right? So step 1, the lines function, takes a string and divides it, computes a string list, which is one entry for each line. And so you can kind of start to get a feel for the fact that like, well, if I'm taking a list and producing a list with the same length where I've transformed every element, then that's probably a map. So what I want to do is map something on the lines. And so what I need to think about is, well, what I need here is a word count function that counts the number of words in a single string. So I can just list that as a subgoal, that I need to write a word count function that takes s, which is a string, and gives you back an int. And for example, the word count of the quick brown fox is supposed to be 4, right? So I'm giving you the number of words in a string. Okay, and so like step 2 goes like that, as long as we then go back and write a word count function. And so now for step 3, I want to take the biggest, but we already wrote that up above, right? So the max L, which was written with reduce, was to take the biggest. Looks like that, right? So I take the max of that. And then if I delete all of my little step signs here and kind of merge them to one line, right, then that's a pretty nice, concise expression of what we're doing, right? So we said that step 1 was to take the lines. Okay, we use the lines function. Step 2 was to word count each line. Okay, we write a word count function and then we map it. And step 3 was to take the biggest. Well, up there with reduce, we had already done an example that was like that. Okay, so now we just need the word count function and we can apply the same process, right? So if I want to do word count, then I can divide into words, and the slick way of doing it is to take the length. So word count is the length of words of S. And then if I balance my parentheses there, then longest line length of the quick brown fox jumped over is 4. Great, we got what we wanted. The sly dog is now 5 because now the second line is longer. Okay, so the thing I want you to take away from this is that we can write a program by just chaining together phases. So for word count, step 1, we divide into words. Step 2, well, the number of words is the length of the division into words. For longest line length, step 1 is to divide into lines. Step 2 is to count the number of words in each line. Step 3 is to take the biggest. Step 1 turns into a function. Step 2 turns into a function, in this case, map of word count. Step 3 turns into a function, in this case, reduce of such and such. And so if we wanted to, right, so like imagine we hadn't written any of these helpers, we could, if we want, expand out max L like that, and expand out word count as the function that sends a string to the length of words of the string. And we still get the right answer there. Okay, so the point is that aside from these basic string manipulation things, which are coming from the library, because like there's some library function that divides a string up into pieces based on characters that you tell it about. In the case of words, it's dividing it up based on spaces or new lines. In the case of lines, it's dividing it up based on new lines. Okay, so there's some library magic there, but other than that, all of this program is just library magic, and then a map of a particular function, and then a reduce. So chaining together a map and a reduce again is like letting us write this function without doing recursion and stuff like that. We're just deploying these patterns, these loops that we've abstracted as higher order functions. We're just deploying them and writing the program by chaining together a pipeline of these higher order functions to step by step achieve what we wanted to achieve.